Today's colloquium speaker is Erez Berg. When I first came to Stanford, Erez came as a student, and I realized I landed in heaven, that all students were going to be exactly like Erez. All faculty members, I would like to take credit for everything he's done. This is, of course, not legal, but I do it anyway. Erez is a professor of physics at the University of Chicago. He was a professor of physics at Weizmann Institute in Israel. And before that, he was a postdoc at Harvard. And before that, he was a student here. I have looked up. We wrote 23 papers together. I think they all have him as the first author for good reason. And he's won all sorts of prizes, but I don't understand them. They're written either in Hebrew or in Chicago. And, so at any rate, it's really great to have him here.
Right. So, I would like to also boast about some of these prizes, but I can't translate them for you. So unfortunately, I can't. So it's a great pleasure to be here. I was a student here, and I've been those who know me, I've been a very frequent visitor here, and each time it's a lot of fun. So this is work that I've been doing for several years now, and it's become quite an international project. So it's been done with this list of highly respected people, but I'd like to highlight especially these three young people. So Sam, who was also a student here, is now a postdoc at MIT. Yoni, who's somewhere there. There he is. He was my student at Weizmann and now is here as a postdoc. And Xiao Yu, who was a student at Minnesota and now is a postdoc in Chicago. So just to set the stage, this talk is going to be about critical phenomena. So critical phenomena is all about scale invariance. So I thought I'll start by talking a little bit about that. And there's kind of a nice pictorial way to show what that is. Okay, but before I do that, we just mentioned that in particular, I'm interested in quantum phase transitions. That is, transitions that occur at a zero temperature between ground states, and in insulating systems, these kind of quantum phase transitions are actually pretty well understood. On the other hand, in metallic systems, in systems that have a Fermi surface, the problem is actually much more difficult and much more rich, and this is what this talk is going to be about. Okay, so this is an outline, so I'll talk a little bit about classical and quantum criticality in general. Then I'll focus on quantum criticality in systems that have a Fermi surface, and I'll describe our approach to the problem, which is numerical quantum Monte Carlo experiments, and I'll show some of the results. They discuss some of our intermediate conclusions and some of the mysteries as I see them. Okay, so I'll start from criticality. So scale invariance. Okay, so found this nice demonstration. So what I'm going to show you is 4 different snapshots of configurations of spins of the Ising model, the 2D Ising model, at its critical point. And the task would be to guess. So these 4 pictures are actually from the same simulation. Okay, you just take a snapshot of all the spins. Spin up would be black, spin down would be white. And the challenge is to guess which picture is taken from which scale. Okay, so that's what this demonstration is about. Okay, so it's scales varying by 2 to the power 6, and here they are. Okay, so they look kind of the same. Okay, but it turns out that they're actually embedded in each other. Okay, so this is scale invariance. Okay, so they really morally look the same. The picture, it looks the same in any scale that you look at it. Okay, so that's this interesting observation, and systems tend to do this when you tune them to their critical point. Okay, they basically forget about the microscopic scale, the correlation length diverges, and they acquire this new symmetry, which is scale symmetry. Okay, and more formally, this symmetry manifests itself in these properties, scaling properties of all the correlation functions. Okay, so they can all be scaled in these types of forms. Now, this is by now very well understood. We know that this emergent scale symmetry is actually just a subgroup of a much bigger symmetry that often emerges at these type of critical points, which is conformal symmetry, that is any symmetry that preserves angles. And these types of critical phenomena are very well understood using a normalization group backed by classical Monte Carlo simulations, and we really know a lot about the possible universality classes of phase transitions. Okay, so there's a universality that means that when the correlation length diverges, the system tends to forget all the microscopic details, and for instance, these critical exponents would depend only on things like symmetry of the order parameter, dimensionality. Okay, these are all very important concepts, not just in condensed matter physics, but also in field theory. Okay, so this was all classical. These are thermal transitions. What about t equals 0 transitions? Okay, these are quantum phase transitions. So what's actually different about them? So the sort of canonical example for this is the transverse field Ising model. If you know what that is, good. If you don't, it doesn't really matter. It's some sort of a model of a lattice model of quantum mechanical spins. And now at temperature 0, there's a tuning parameter that you can tune and take this model from the ordered phase to the disordered phase. What's driving this transition is not thermal fluctuations, it's actually the 0-point motion or quantum fluctuations of the spins. Okay, so here's this parameter. It's called the transverse field. It controls the amount of degree of quantum fluctuations in the system. And as you tune it, you go from the ordered phase to the disordered phase. Okay, the spins start fluctuating quantum mechanically more and more until the order parameter vanishes. Okay, and you can say, well, this is at temperature 0. This is really a transition that happens in the ground state of the system. And of course, no experiment is actually in the ground state. We're always at some finite temperature. So why do we even care about this kind of a theoretical concept of a quantum phase transition? And the reason is that this actually has a very strong imprint on the behavior of the system at finite temperature. Okay, so this is the temperature axis. This is the region we can actually access in real life. And what would happen is that because of the fact that the system has lost all or forgot about all the microscopic scales here, you introduce the temperature, and that's going to be the only scale in the system. So basically, physical quantity are all going to scale with the temperature or the frequency in which you probe the system with critical exponents that are actually characteristic of the underlying quantum phase transition. Okay, a critical point. So that's why we care. Okay, now it turns out that you can understand quite a lot about these kind of zero temperature transitions just by mapping them into classical transitions in one dimension higher. I want to explain that a little bit. That's very fundamental to our thinking about these kind of problems. Okay, so it turns out that quite generally you can map a d-dimensional quantum problem, that is a quantum critical point in d spatial dimensions, into an equivalent classical problem in one dimension higher. Okay, and what this extra dimension is basically time. So the time dimension, it describes the quantum fluctuations of the order parameter. Okay, so this is our Ising magnet, and this is position, and this is time. Okay, so the difference between the ordered and the disordered phase is that in the ordered phase, the spins fluctuate a little bit, but on average, they still point in one direction. In the disordered phase, they're random. Okay, so for many purposes, it turns out that you can actually do this mapping exactly, and you can simply read off the critical exponents of the quantum mechanical problem from the corresponding classical problem in one dimension higher. Okay, there's one important difference. The extent of this time or imaginary time direction is actually finite. Okay, it's not infinite. Usually we take the thermodynamic limit in all the spatial directions, but this is going to be finite, and the extent of that is going to be simply 1 over temperature in the right units. Okay, and you notice that this time direction is actually proportional to h bar. So in the classical limit, this would collapse, and you would go back to the corresponding classical transition at the fixed temperature. Okay, so with that difference, so it looks like we can actually understand a lot about quantum phase transitions just from knowing the theory of classical transitions. So what's actually the difference? Okay, is there any difference, or is it all the story? So first of all, it turns out that this mapping, even though formally it's always doable, it doesn't always work in the following sense. Okay, so the a classical partition function would give you a probability for every space-time configuration like this. Okay, so that's basically the Gibbs weight. However, in quantum mechanics, every space-time configuration like this gets a value which is a quantum mechanical amplitude. Okay, so in general that has both a modulus and a phase. And if that phase varies between different configurations, that means that the problem in some sense is truly quantum mechanical. It cannot really be mapped into a corresponding purely classical problem. Okay, so there's a lot of richness that can come in from these types of phases. They're called Berry phases, and they give rise to phase transitions that are truly quantum mechanical, have no classical analog, not even in a different dimension. Okay, so that's one type of a uniquely quantum mechanical phenomena you can get at critical points. Okay, so I'm going to talk about another one, but the world of quantum phase transitions is actually much richer, and there's a lot of examples that we understand at 2 various levels of these types of exotic quantum transitions. Unfortunately, no experimental examples that I know of, but the theory of that is pretty well understood. People have been looking for that pretty hard, especially in numerical experiments. Okay, so now let me move to a different kind of quantum critical points, that is quantum critical points in metallic systems. Okay, so far I assume that there are no itinerant electrons in the system. Now I'm going to talk about the Fermi surface, a system with a Fermi surface that undergoes a quantum critical point, and what extra richness does that bring? Okay, so first of all, before we talk about a critical metal, let's talk about a conventional metal. So that's actually fairly well understood. So if you have a metal like copper, so what's the ground state and what are the basic low energy excitations of the system, so that we understand very well. Even though the system might be very strongly interacting, it turns out that the low energy description is actually pretty close to the description in terms of free fermions, free quasi-particles that are almost like electrons. Okay, so the ground state is a filled Fermi sea, and the low energy excitations would be just described by adding one electron, one fermion, at an energy very close to the Fermi energy, and that's not quite a free electron. It would have this long trail that it would drag along with it because of the strong interactions, but it can still nevertheless move freely, almost like a free particle. Okay, so that's basically our description. This is called a Landau Fermi liquid. It's a very elaborate and beautiful theory of a conventional metal. Okay, and it has many confirmed predictions. Okay, so this is the quasi-particle. This is the Fermi sea. Here's a slightly more conventional picture. So we draw the Fermi surface as a function of a momentum kx and ky. This is the Brillouin zone of the crystal. Okay, and this would be the filled Fermi sea. There's a sharp surface at temperature 0. Okay, it becomes slightly thermally smeared at finite temperature, but at temperature 0, this is really a singularity, surface of singularity in k-space, which separates the filled states and the empty states. Okay, and these are the excitations of the systems. These will be the quasi-particles and quasi-holes that are almost like free particles. Okay, so now the interesting thing. Okay, so this looks kind of simple, kind of trivial, but this Fermi surface is actually a quantum mechanical object. Okay, so it really owes its existence to the Pauli principle, and it has no classical analog. Okay, so there's no sort of simple semi-classical way to capture that. And what this talk is going to be about is what happens when such a system that has a Fermi surface, so that has a whole surface in K-space where low energy excitations live, undergoes a critical point. Okay, so at the critical point there's going to be some order parameter which is just about to order. It has a lot of long-range fluctuations, and these fluctuations are going to be coupled to fermions close to the Fermi surface. Okay, so these are these scale invariant fluctuations. The Fermi surface is going to respond to these types of fluctuations. For instance, it might move depending on the space-time configuration of the order parameter. And as a result, what might happen, for instance, is that this sharp Fermi surface might smear, and we will get a new type of metal, a non-Fermi liquid metal. Okay, so this is the types of states we might encounter when we follow a metal through a quantum critical point. And just to show you that this is not completely disconnected from real materials, okay, so this type of phenomena has been discussed in many different families of materials, but in particular I'd like to mention high temperature superconductors. Okay, so the cuprate superconductors have been discovered more than 30 years ago. This is the phase diagram. It's very, very complex. Don't notice all the details here. Let me just say this axis is a composition of the material. Okay, some dopant, some atom that you substitute, and this is temperature. And these are all the different phases that you get. And here's another family that was actually discovered much more recently, 2008, of iron-based superconductors. Okay, but once again, this is composition temperature, and maybe you notice kind of that even though these are totally different materials microscopically, there's some similarities in the phase diagrams. Okay, there's a magnetic phase that can be tuned down essentially to zero temperature as a function of composition. Okay, here it is here or there, and when it vanishes, it undergoes, presumably there's a quantum phase transition somewhere here, and there's a superconducting region in the phase diagram or dome that kind of encloses the region of this putative quantum critical point. Okay, so there's no accepted theory. There's even no consensus about what consists exactly of a theory of these very complex materials. One thing, definitely everybody agrees that they're very, very complex. Okay, but it's clear from these diagrams that there are many ordered competing or cooperating phases in these phase diagrams that all have a complex interplay with each other. And these different phases undergo various transitions, including quantum transitions at t goes to 0 from one to another. Okay, so that's fairly clear. Now, I haven't explained the color plot here. Okay, I won't explain that. We won't go into details, but this is some quantity. It's basically the exponent of the resistivity with temperature. Okay, some property of the metallic state in the normal state above Tc. Okay, and you can sort of broadly notice this type of fan shape red region. Okay, so this exponent it takes a value of 2 in a conventional metal. So this region, for instance, this is believed to be just a conventional, essentially a conventional Fermi liquid metal, and it crosses over to this red phenyl, which is some sort of new type of metallic behavior that we don't quite understand, but seems to emanate from the vicinity of the putative quantum phase transition. Okay, so these types of phase diagrams led for a long time to a natural question: is there a fundamental role of these quantum critical points, the way I've explained before, that they actually control some region of the phase diagram at finite temperature? And maybe they can explain some of the exotic phenomena. So here you see a phase called a strange metal. That's once again, that's some sort of unconventional metallic behavior. By the way, these two have in common that the resistivity is a linear function of temperature in both of these unusual regimes. And this is a new beast. This is a new kind of metal that there's no good theory of, and may or may not be tied to quantum criticality, and that's what we're after. That's what we want to understand here. Okay, this question has been around for a very long time. Okay, and just to make connection with the models that I'll be studying, let me just focus on one of these materials. This is an iron-based material, and this is its phase diagram. You see, once again, as a function of composition and temperature, there's a magnetic phase that is suppressed to 0 and gives rise to a superconducting region. Okay, but this magnetism actually has a special form. Okay, if you look at the lattice of iron atoms, it would look like this. So, okay, they're parallel to each other along rows, and different rows have an opposite direction of the moment. But the underlying lattice is actually a perfect square lattice. Okay, so you see that when the state becomes ordered, when the system becomes magnetically ordered, it has to choose both the direction of the moment, but also the direction of these rows. Okay, there are actually two symmetry equivalent states that the system has to choose from. So these are two separate symmetries that the system breaks, and these two symmetries don't have to be broken together. Okay, so you see actually there are two phase boundaries here. Okay, so this one is when the system chooses the spatial direction, x versus y, but still doesn't magnetically order, and only at a lower temperature, there's a separation of order of about 10 degrees Kelvin. There's another transition where the moments actually become non-zero. Okay, and you see that both of these transition temperatures are suppressed as a function of x. We don't know exactly what happens down here, but if you extrapolate, it looks like they would actually hit 0 at some value of x. So these would be quantum critical points. Maybe they're merged actually at a very low temperature. Maybe it goes first order. We don't really know. Okay, but you could imagine that if you extend this phase diagram somewhere in a slightly bigger phase diagram, there would be two separate critical points. And the question is, what's their role in this physics? Okay, so these are actually the two types of critical points that I'm going to study in this work. Okay, so I'm going to separate the problem. I'm going to pretend that there's only one or the other type of order in the system. So these are going to be different kinds of critical points depending on properties of the symmetry which is broken, and each one would have its own properties. Okay, so the full thing would be to understand how they interplay with each other, but for now let's try to separate variables. Okay, so the first one is this kind of symmetry breaking where a square lattice spontaneously breaks its symmetry and chooses a direction, either x or y. So before the transition, we would have this symmetric Fermi surface, and at the transition, what happens is that the lattice distorts, x becomes inequivalent to y, and at the same time, the Fermi surface of the system would also respond by symmetry. It would not be perfectly rotationally symmetric anymore. It would be elongated either along x or y. Okay, so there's a very strong coupling then between the direction of the order parameter and the shape of the Fermi surface. The whole Fermi surface would distort, except for these 4 points which are dictated by symmetry, basically by the form factor of the order parameter, where the Fermi surface is actually stationary. Okay, so at these 4 points, the Fermi surface doesn't move. And we'll see that's going to be important later. Okay, and the other type of critical point is going to be a metal which is undergoing a critical point to a magnetically ordered state in some finite wave vector, like this spin density wave. Okay, so in the ordered state, the average magnetic moment on every site is 0. In the disordered phase, in the ordered phase, it actually acquires a non-zero value. Okay, and because this occurs at the finite wave vector, so these moments are modulated in space, their average is 0. This type of order parameter would actually scatter fermions very strongly, close to the critical point, at this wave vector. So you see that if you examine the Fermi surface, there would be some special points on the Fermi surface where you can resonantly scatter an electron where both the initial and final states are on the Fermi surface. So here this interaction is going to be resonant, whereas anywhere else a scattering from the surface would take you somewhere away from the Fermi surface. Okay, so these points are going to play an important role. These are so-called hotspots where the interaction is most important. Okay, so these are the two types of critical points I want to study. Okay, so what are the kinds of questions that we'd like to answer about such critical points? Okay, so we want to know if their properties are universal in any way. If they are, what are the universal critical exponents that describe these critical points? Is the Fermi surface really destroyed and gives rise to some new type of metallic state? And what are the how do we describe such a metal? Okay, this what we expect is that if such a metal arises, it's not described by nearly free quasiparticles anymore, because the quasiparticles scatter very, very strongly off the fluctuations of the order parameter. Okay, so how do we describe such an unusual metal? Okay, so and another important question that arises is basically the following. So we saw in the materials very often the putative quantum critical point is actually hidden under a superconducting phase. Okay, and there's a natural way to understand how that can arise. If there's strong coupling between the order parameter fluctuations and the electrons, the fluctuations can mediate attractive interactions between the electrons, and once electrons on the Fermi surface are attracted, they naturally give rise to a superconductor. So we expect actually superconductivity to be enhanced in the vicinity of the quantum critical point. Okay, but this is actually turns out to be a very complex problem. The reason is that there's a competition here between two opposing effects. The fluctuations tend to bind the electrons together. At the same time, they also scatter the electrons very strongly, and the electrons lose their coherence, and that actually harms superconductivity. So basically, which of the two effects wins? That's an important question. Okay, and it might, for instance, be that electrons are paired so strongly that the superconducting phase would actually always enclose the whole critical region, and the electrons don't even get a chance to form some sort of new metallic state. So this is sort of one scenario where the electrons are still coherent above the superconducting transition, or maybe there's a well-developed a new metallic state, non-Fermi liquid, which actually the superconductor actually emerges out of. Okay, so whereas if you go away from the quantum critical point, you recover the usual Fermi liquid behavior. Okay, so this problem has been studied for generations, pretty much. Okay, so some very distinguished theorists have worked on this. But it turns out that the bottom line is that this is actually a strongly coupled problem. Okay, there's no easy expansion parameter we can use to expand in, and therefore this problem is not fully understood. Okay, so there still are debates about basically all these questions. Okay, so the approach that we took to this problem is numerical. Basically, we want to design some simple models, lattice models, and then hope there's some sort of universality, so such that the details of the lattice model don't matter, and tune the lattice model into a critical point, and then we can just watch what happens. Okay, we basically solve these models numerically exactly. Models that have a Fermi surface, okay, and nevertheless can be simulated, and right, and see to what extent we can answer the questions I've presented. Okay, so what type of models I'm going to introduce? Okay, so let me lead you through that. Okay, so I'm going to introduce some sort of lattice model where on every site there are two types of degrees of freedom, representing the two low energy degrees of freedom that I expect to play an important role in this problem. Okay, so one is the order parameter, who's about to order. Okay, so I have space-time fluctuations of this field phi describing the order parameter, and the other are fermions that form a Fermi surface. Okay, so these are the two types of low energy degrees of freedom that are interplaying. One is basically electrons and holes close to the Fermi surface, and the other is the order parameter fluctuations. And this is the type of quantum action that people write to describe this problem. So there's some action of the fermions that I'm simply going to take to be free fermions, okay, to form this Fermi surface. There's an action of the order parameter, and there's some interaction term that couples them. Okay, this is the action of the fermions, simply free fermions. This is the action of the boson. It's basically an expansion in the amplitude and in the gradients of the order parameter, okay, assuming that near the transition the order parameter is small and its spatial and temporal variations are slow. And this is the type of, schematically, this is the type of interaction that couples the two. Okay, so it's linear in the order parameter and quadratic in the fermions. This would have an appropriate symmetry form, so the order parameter would couple to the correct quadratic term according to the type of symmetry that it breaks. Okay, and there's a coupling constant in the problem, which is the coefficient of this interaction term. This is so-called Yukawa term. That determines how strongly these two are basically interacting with each other. Okay, so this is a field theory, which is sort of the naive continuum limit of this lattice model that I'm writing. Okay, but I don't formulate it in this continuum form. I actually form it on a lattice. Okay, and the question is how do we solve such a problem? This is obviously an interacting problem because of this cubic term. And it turns out that perturbation theory in this small parameter, even though it can definitely take you pretty far, is ultimately uncontrolled in trying to determine the properties of this quantum critical point. So how do we proceed? Okay, clearly we need a non-perturbative method to solve this problem. And there are only so many methods to really solve an interacting many-body quantum problem. Okay, unfortunately, we don't have a lot of tools there. The method of choice is a so-called determinant quantum Monte Carlo. So let me spend a few minutes explaining how that works. Okay, so we want to do Monte Carlo on a quantum problem. This problem involves fermions, and fermions are described by Grassmann numbers. We don't know how to sample Grassmann numbers. So we first integrate them out, and we can do that exactly because the action I've presented is actually quadratic in the fermionic degrees of freedom. So for every space-time configuration of the bosonic field, we integrate out the fermions exactly, and we get some effective action, which is basically the bare action of the order parameter times whatever we get by integrating out the fermions, which is basically the determinant of some matrix. Okay, so we write this. This is some functional of the space-time fluctuations of the order parameter. Okay, for every such a configuration, you get here a number, and this looks just like a Boltzmann weight. Okay, so you might think, well, by now we've actually mapped the quantum problem into some equivalent classical problem with one dimension higher, this is time. And now we can just apply the usual trick, which is classical Monte Carlo, to sample over this effective action. Okay, so the trouble is that because of the fact that we're dealing with fermions, when we integrate them out, we're not guaranteed to get basically a real action here. The action can be imaginary, or this Boltzmann weight can have a phase. It's a quantum amplitude. So this is the so-called fermion sign problem. Okay, so basically, whenever this amplitude is complex, you say that you have a sign problem. You can't quite sample complex numbers. At best, you can sample over the modulus of this complex number. Treat that as your weight or your probability. But it turns out that can only take you so far. That method actually fails at very low temperatures. The question is, what do you do next? So there are some problems where it turns out that this fermion determinant is actually positive. okay, or a real and non-negative number. And that's very fortunate because when that happens, then the problem is essentially solved. Okay, then you can really treat this as a probability and apply classical Monte Carlo, which is very efficient. So these will be sign-free problems. And let me give you an example of such a problem. If both spins of electrons, spin up and spin down, are both coupled to the same bosonic field in the same way, then when you integrate the fermions out, you basically get a product of two determinants, one for spin up and the other for spin down. They're the same, so you get just a square, and they're both real because basically there are no complex numbers in this particular problem. And then you get that this is a square of a real number, so clearly it's non-negative. Okay, but the pneumatic problem that I've described, the Ising pneumatic problem where you have an order parameter that breaks the symmetry between x and y, is actually precisely of this family because that type of order parameter couples in the same way to spin up and spin down. Okay, so this is that problem, we're actually lucky. That problem would not have a sign problem. What about the case of the antiferromagnet? Here we're actually not as lucky. So here, because it's a magnetic order parameter, it couples differently to spin up and spin down. And here this simple reasoning doesn't work. And it turns out that this actually has a hard sign problem, meaning that you get phases or plus and minus with more or less equal probability. Okay, and that's sort of been a roadblock for a long time. But there's a trick. Okay, what we argued before is that the important physics is taking place in the vicinity of these hotspots. Okay, so these are the only points on the Fermi surface where electrons can scatter resonantly. So that kind of implies that if there is a quantum critical point with universal properties, its properties are basically determined not by the entire Fermi surface, but just from the vicinity of these points. Okay, that's a physical argument. It definitely happens in perturbative calculations, and we're going to believe that for now. Okay, so that means that we don't care about the properties of the Fermi surface far away from these special points. We can play with the Fermi surface however we want. For instance, we can take a different model that has two flavors or two bands of electrons, okay, blue and red, and each one of them has its own Fermi surface, but the shape of the Fermi surface is, as it was before, close to these hotspots. And it turns out that this type of doubling of the number of the degrees of freedom actually guarantees that the fermion determinant would be non-negative. Okay, so there's some sort of effective time reversal symmetry that guarantees that, and this problem is actually sign-free. So we can actually do simulations on this type of modified model with two types of electrons, both coupled to the same order parameter antiferromagnetic field. Okay, so this is our program. So that's what we're going to do. We're going to solve these two models, and in the rest of my time, I'd like to show you some of the results and discuss some of the conclusions. How much time do I have?
20 minutes, I guess.
Right. Yes. Okay. Right. Okay, so here are some results. So I'll start from the Ising pneumatic critical point. Okay, we've done extensive simulations on some lattice model that undergoes such a transition. I won't write the model explicitly, but I'll just try to flash out some of its properties. So first of all, the phase diagram. Okay, so we draw the phase diagram as a function of two parameters. One of them is a parameter we called h. That's a tuning parameter in the Hamiltonian. It's just like the transverse field I've described before. It's something that controls the quantum fluctuations of the order parameter. Okay, the higher it is, the more fluctuations the order parameter has. And the second is temperature. They're both written in units of V, which is some microscopic interaction. Okay, so as a function of h and v, there is an ordered phase. This is the pneumatic phase where x or y become x and y become spontaneously inequivalent, and this phase boundary separates the pneumatic phase from the disordered phase where x and y are the same. Okay, and this transition temperature, which is measured here numerically, collapses to 0 at a value of h that we would extrapolate somewhere here. Okay, so there is indeed a apparently second order quantum phase transition in this model that we can access. And we expect there to be some sort of quantum critical regime where there are strong quantum critical fluctuations at this kind of fan-shaped region emanating from this critical point. Okay, and there's also some crossover that we characterize, which is kind of roughly the end of this fan into a more conventional non-critical metallic phase. Okay, so now what happens down here? In this simulation, it was actually hard to tell. Okay, we couldn't reach low enough temperatures. But what we can do is we can increase the value of the coupling constant between the fermions and the order parameter fluctuations, and that kind of boosts up all the energy scales. So then what we see is that actually around this putative quantum critical point, what we get is a superconducting phase in this dome-shaped region, which where the superconducting TC is actually highest, roughly where you would extrapolate the pneumatic transition to zero temperature. Okay, so indeed this quantum critical point is covered by a superconducting region, and TC, the maximum TC, increases with the value of alpha. Okay, we also have one intermediate value of alpha. Okay, so now we'd like to know what are the properties of this quantum critical regime? Okay, so how do we characterize the system in the vicinity of the quantum critical point? So we can characterize the system in different ways. For instance, we can look at correlations of the order parameter at different space and time points and see how these correlations grow as we approach the quantum critical point. Okay, so it turns out that if you look at static correlations, that means zero frequency correlation functions of the order parameter, they actually can be summarized by a very simple functional form that you can collapse a lot of data to. Okay, so this very simple functional form, it's a Curie type form suggesting some sort of mean field behavior. Okay, so this was very beautiful, but it turns out that if you look at the Q and the wave vector and frequency dependence of these correlations, they're actually more complex. We couldn't find a simple a functional form that would collapse all of them. Okay, maybe I'll get into that, back into that in a little bit. But at the same time, we want to look at the fermions, at the electrons close to the Fermi surface and see what they're doing. Okay, so the way we characterize these is through the spectral function that we can characterize. This is basically the low energy electronic spectral weight, and we can calculate that directly from our imaginary time data. Basically what we can access is this integral of the spectral function around the Fermi energy. Okay, so this is some integrated spectral weight in a window of order temperature around the Fermi energy. So what does that look like? If we go far away from the critical point, okay, so back here, it's 5.5, okay, so somewhere there. What we expect to find is basically a conventional metal. And this is what this low energy spectral weight looks like. It's peaked, strongly peaked on the Fermi surface. Okay, but when you approach the critical regime, this is at finite temperature, H close to HC, this is what you find. Okay, so there still are well-defined peaks and regions on the Fermi surface that look well-defined along the diagonal direction in K-space. Okay, so these regions. But far from the diagonal, there are actually these kind of blurred regions where you can't even identify a simple line. Okay, where is the Fermi surface here? Okay, the reason for this anisotropy we actually understand. This is precisely these cold spots. Okay, so along the diagonals, to leading order, the coupling between the fermions and the order parameter fluctuations vanishes. So we actually expect it to have the least effect on the diagonal and a maximum effect along Kx or Ky. Okay, so what's going on here is that the order parameter fluctuates a lot. For every configuration of the order parameter, there's a different Fermi surface, and this is what you get basically from averaging over these space-time fluctuations. Okay, so no well-defined Fermi surface really in these regions, so this looks a lot like the sort of non-Fermi liquid, a new type of metal that we've been looking for. Okay, so there's a precise way to characterize that for the experts. We look at the self-energy that we can measure as a function of imaginary frequency, Matsubara frequency, and that has actually a very surprising behavior that we didn't expect. It can be summarized very simply. So the self-energy is simply a constant, independent of both frequency and temperature. So this is really not what we expect but from scattering from a dynamical order parameter. It looks more like scattering from static disorder, which really is not present in this problem. Okay, so this is something we're still struggling to understand. Okay, so that's a first look at this phase diagram. Now, unfortunately, we can't go as low as we want. Okay, so we want to characterize this quantum critical regime, but it actually doesn't exist all the way to zero temperature. What we're doing is just exploring the crossover here. So unfortunately, there are many questions we'd like to answer, and we can't give quite sharp answers to, because to give a sharp answer, you need to be able to access as many decades of temperature as you want. And unfortunately, we don't have that luxury here. Okay, the ground state is actually never this metallic state. It's always the superconductor. And that's a nuisance for us. Okay, other than the fact that it's interesting that we find superconductivity, which is enhanced. But unfortunately, we don't know yet how to suppress this superconductor in our simulations. Experimentalists do this by applying a magnetic field. Okay, and that's a very natural way to explore the underlying non-superconducting state, but we can't do that in our simulations. It causes a sign problem. Okay, so that's an unfortunate fact. But given that, okay, we do find some interesting properties. And what about the resistivity in this new type of metallic state? Okay, so we've seen that very often what arises in materials is resistivity, which is a linear function of temperature in this critical regime. And does that happen in our simulation? Okay, so that's an important question. Now, unfortunately, we can't answer that directly in our simulations. The reason is that to calculate conductivity, you really have to go to a low but finite frequency. It's a dynamical property. Okay, you have to excite the electrons as a function of time. And in our simulations are all done in a Matsubara frequency or imaginary time, and it turns out that even though all the information in principle is there, it's very hard to actually extract the real-time information from the imaginary time data. Small error bars in the imaginary time data translate into huge error bars in real time. So we can't quite tell you what the resistivity is. However, we can define a resistivity proxy, which is not correct here, but some variant of this. Okay, what it is basically the following. You can think about it as follows. What the imaginary time gives you is data which is smeared over an energy range of order the temperature. Okay, actually of order pi times the temperature. The reason for that is precisely that the imaginary time extends up to a maximum time of 1 over temperature. So this is your intrinsic resolution on any frequency scale. Okay, so what you get is not the conductivity. It's basically some sort of average over the frequency-dependent conductivity over this energy scale of order temperature. Okay, so under some assumptions, for instance, if the conductivity consists of just a single peak, and this is where this is not quite right, we can also measure the second moment of this peak. Okay, so we can say something about its width and its overall weight. So if we assume that there's only one simple peak and no further structure in this low temperature window, we can actually deduce pretty well what the actual static DC conductivity or resistivity is. Okay, however, if there's much more complicated structure within this window, then unfortunately we smear that completely. It's below our resolution, if you like, and we can't tell. Okay, so this is the crucial assumption we're making. Okay, so now let's make it. And let's plot this resistivity proxy across the phase diagram. This is what it looks like. Okay, so this is a color plot. Now, notice it's not quite the same as before. It's not an exponent. This is the actual value of the resistivity in kind of natural units of h bar over e squared for a 2D system. Okay, so what you see here is that the resistivity has this strong maximum sort of centered in the quantum critical fan region, where the quantum fluctuations of the order parameter are strongest, actually quantum and classical fluctuations. Okay, and if we look at the resistivity as a function of temperature along these three cuts, okay, at fixed values of the tuning parameter, this is what it looks like. Okay, so if we're deep in the disordered phase or in the ordered phase, the resistivity is low. Okay, the value itself is low. We can't quite tell too much about this. Okay, our method becomes very inaccurate when the resistivity is small, but it's very high over here. Okay, so this is this curve, and with a little bit of loving eye, this is linear-ish. Okay, and it looks like this metallic state, if this assumption is correct, does indeed have a linear in T resistivity, or something that looks like that. Okay, and this is actually a very surprising result. Actually, we and other people really didn't expect this. The reason is the following. So the pneumatic order parameter fluctuates as very small momenta because it's about to order actually at zero momentum. It's in the ordered phase, it's uniform in space. So you would expect it to scatter fermions basically by a very small wave vector. And this means that it actually won't, it might affect the coherence of fermions very strongly, but it won't affect the value of the resistivity very strongly, because if you scatter by a very small angle, you don't change the velocity of the electrons very much, and that's the thing that determines the resistivity. Okay, but here we actually see a huge effect on the resistivity under this assumption, if you believe this one, with this sort of featureless conductivity on a scale of temperature, then there's actually a huge enhancement of the resistivity in the quantum critical regime. Now, how do you understand this kind of disagreement with basically with theory? So one explanation is simply that this assumption is incorrect, okay, and that there's actually much more structure in sigma of omega at much lower frequencies than what we can probe, and actually at zero frequency there's a big peak in the conductivity, meaning the resistivity is actually much lower than what we think. But there's another explanation that we're kind of excited about, but that still requires a further study. Okay, so let me just flash this kind of pictorial resemblance while passing. Okay, so if you look at the correlation functions of the order parameter in this quantum critical regime at strong coupling, which is where these measurements of the resistivity were taken, they actually have a very unusual character. They become basically more and more local in space. Okay, so what that means is that the fluctuations are very weakly correlated between spatial points, but have a very long correlation time. Okay, the fluctuations are mostly in time. This is what some cuts look like. Okay, so this is the correlator of the pneumatic order parameter at different frequencies as a function of Q, and you see that up to a sort of almost quarter of the Brillouin zone, it's ever except at the smallest frequencies, it's actually pretty flat. And this is the opposite plot. This is a different momenta as a function of frequency, and they all sort of collapse onto each other. The pneumatic susceptibility hardly actually depends on momentum. So these types of type of local fluctuations are very unusual. Okay, this is sometimes called local quantum criticality, has been proposed, but there's no good theory for that. And in particular, it can give you very easily, it can give you a large value of the resistivity, because if these fluctuations occur at large momenta, they can scatter the electrons by a large angle. Okay, but we're still studying whether this is, to what extent this is really the case, and what can be the origin of this type of behavior. Okay, so this local type of local quantum critical point has come up in many different contexts with different mechanisms, and it would be really exciting if this is the case here. Okay, so maybe in the remaining few minutes, I'll just flash a few results for the other type of critical point, for the antiferromagnetic critical point. Okay, so first of all, the phase diagram. So we basically repeat the same analysis, but for an antiferromagnetic quantum critical point. These are different phase diagrams for different values of the Yukawa coupling, which here is called lambda. Okay, and you see there's a magnetically ordered phase which collapses as a function of our tuning parameter. And again, it's covered always by this superconducting phase. It's a different kind of superconductor. It has a different symmetry. This is actually a D-wave superconductor, and in the previous case it was S-wave, but nevertheless, we can never reach here a bare quantum critical point. Okay, and we've actually studied in quite a lot of detail, this is an ongoing study, what actually determines the maximum TC in this system. Okay, so suppose we were asking, suppose I can design for you a material undergoing an antiferromagnetic quantum critical point. What properties should this material, for instance, the band structure, have to maximize TC? Okay, and it turns out that TC in particular is very sensitive to properties of the Fermi surface, in particular very close to these hotspots. Okay, so it's very sensitive to the angle in which the Fermi surface shifted by Q meets itself. Okay, so we've kind of designed a family of Fermi surfaces where this angle varies, and it turns out that TC basically goes as the sine in these simulations, goes as the sine of this angle. Okay, so this is exciting for two reasons. First of all, it gives us some insight into the mechanism of what determines TC, and second, it looks like if we take this angle to be zero, namely almost parallel Fermi surfaces, this might give us a route to suppress TC very, very strongly. Okay, so this might actually give us access to the actual quantum critical point in the metallic state, in the non-superconducting state. Okay, so skip this. Okay, we looked at the correlation functions of the magnetic order parameter as a function of frequency, momentum, tuning parameter, and temperature. And it turns out that actually all of this data, okay, this is a few thousand data points, can be collapsed pretty well into this very, very simple form that was actually predicted very long ago. This is a so-called Hertz-Millis theory, a very naive, sort of simple-minded theory. And here it works really beautifully. In the case of the Ising Pneumatic, things are much more complicated. Here, this really describes the data rather well. Okay, and we have some detailed information about what the fermions are doing across the Fermi surface, and they are very weakly scattered away from the hotspots. They kind of are almost coherent, but at the hotspots there's this very strong suppression of the quasi-particle weight, basically the coherence of the quasi-particles. So that's sort of what we expect. But once again, if you look at the self-energy, or the inverse lifetime of the electrons, it's roughly described, pretty well described, simply at the hotspot by simply this formula. Okay, the inverse lifetime is just a constant, which is kind of similar to what we saw in the Pneumatic. Once again, that's not the form we expected, and we're still trying to understand that. Okay, so that's basically it. Let me just flash my conclusions. Okay, so what have we actually learned from this exercise? So I think the zeroth order, and maybe the most important thing, is that these types of metallic quantum critical points can actually be accessed in quantum Monte Carlo simulations without the sign problem. Okay, so we can realize them in well-defined models and study them. Okay, and we've started to look at the properties of these models, and it looks like there are some very robust features or properties that these models have. The quantum critical point tends to be preempted by a high TC superconductor with a dome-shaped TC, which is peaked close to the quantum critical point. Okay, so we actually never get to a bare metallic quantum critical point. The critical point always actually occurs in a superconductor. But if we look at the quantum critical regime, it has interesting properties. The correlations of the order parameter do get to be enhanced quite a lot before that you hit the superconducting phase. And we see evidence for breakdown of Fermi liquid behavior, the formation of some unusual metallic state where the transport is very anomalous. Okay, so what's missing if we compare our results to the materials I've flashed in the beginning? Okay, so there are some things that are, all these things are sort of are good, but there are some qualitative features that we don't see. And that's also interesting because many people have proposed that they arise naturally in the vicinity of these quantum critical points. For instance, there are no other competing orders other than superconductivity that arise naturally if you just tune the system to a critical point. Okay, so all this sort of complex interplay of different ordered phases that arises in the materials is not present here. Or here the only things are the primary order parameter that we put by hand and the superconductivity that actually emerges. There's no pseudo gap. Okay, so in the cuprate superconductors, there's a big region of the phase diagram where there appears to be some gap, gapping out of fermions with no corresponding or no obvious corresponding order, and that's not seen in our simulations. Okay, we see opening of gaps of the fermions, but they're always kind of tied to some sort of nearby ordered phase, either the antiferromagnetic phase or the superconducting phase. Okay, so I think we've actually learned something from that too. And there are many open questions. Okay, how do we determine the DC resistivity more accurately by this procedure called analytic continuation? In principle, there's no accurate way to do that, unfortunately, from our simulations, but we have some ideas how to at least improve the procedure. And one important last point, okay, we're studying these sine-free models. These models, by definition, are very, very highly fine-tuned. Okay, so we tuned basically a lot of possible parameters in the model to get rid of the sine problem. Okay, any small deviation in Hamiltonian space would introduce a sine problem, and we believe that this fine-tuning didn't introduce any artifacts, but this is an open question, really. Okay, and it would be interesting to find a model where we can, there is a sine problem, but somehow we can overcome it. But that's, of course, hard. Okay, so this is a challenge for the future. So, right, I'm basically done, and thanks very much.
Great. Are there questions?
Actually, I have one.
What a shock.
Yeah, what a shock. No. I wonder if you have an opinion about how commonplace these things are in nature. In other words, if I go to the literature, I find hundreds of thousands and perhaps millions of alloys and substances that are metallic.
Right.
And you have a couple of variables, chiefly pressure.
Yes.
And stoichiometry is your other one. So
yes.
Is this happening in 5 materials of the known universe?
Yeah.
Or is it very, very common?
Yeah. So I think it probably happens in thousands out of hundreds of thousands. So it's very rare, but there are many examples. So yeah. So I mean, I think we're kind of looking at a subset. It's a small subset of materials where this happens, and it's not very common. Most metals actually don't have any of this. Right, maybe we're tuning our materials exactly to find this.
Well,
this is where.
If I may just refine the question a little bit. So here you can see the nut of the problem. When you take the temperature down to really get at the nut of the quantum criticality, some phase intervenes.
Yes.
And so it doesn't happen.
Yes.
So this is a counterexample. It doesn't happen in nature in this particular case.
Okay. Yes.
And you've got proximity, but what actually happened was an ordering intervened.
Yes.
In
Yes.
a way.
Yeah.
Now, so if we exclude that,
yes,
those kinds of things, then how pervasive is this in nature?
Right. So definitely even more rare.
Pulling out ones where where there's a low temperature
Intervening phase. Yeah.
Yeah, because yes, and I think just for pedagogical reasons, you'll never really know if you got the quantum mechanics right.
Yes.
Unless you take it all the way to zero, and that means you have to ban any intervening phase.
Yes. Yeah. So I think there are much better examples than this one. So in some cases where you tune the transition by a magnetic field, by a strong magnetic field, there's no superconducting phase, and you actually you have a couple of decades where this doesn't happen. But okay, that's the best people got.
There are hundreds of these. If you tune by pressure, you tune. I mean, it's just that these catch our eyes because of the high temperature. But there are many hundreds with lower temperatures that we are not studying as hard as we study this one because of the high temperature.
yes.
Just in heavy fermions, I mean.
Well,
I
that
can't
was the
remember.
question. Is that what's going on with the whole heavy fermion literature?
So,
Is it really just many examples of stuff like this?
yeah,
I think so.
yeah, and they do always seem to have a superconducting phase.
Well, I mean,
if you go low enough.
well, I mean, if you tune by a
Not
by
magnetic
a
field.
magnetic field, sometimes they don't.
Yeah, but they always
But
have
they
finite
usually have a finite
superconducting
TC close by.
Yeah, the
Yeah.
other thing, of course, that can go wrong, which goes wrong even more often, is the transitions become first order. I mean, there are tons of structural phase transitions that go on at zero temperature, and they're almost all first order.
Yeah, and remind me why this one doesn't become first order? The pneumatic one? It's
It's
commensurate. Why wasn't
Q
it first order?
Q equals 0. Yeah, right.
Of course. Good answer.
So the antiferromagnetic
We
is
were convinced that it would go first order. Erez didn't say the number one thing we were pleased about is that we still had a transition.
so we do have some evidence that at the lowest temperatures the antiferromagnet might be going first order.
Is there a simple qualitative reason that Hertz-Mills theory applies well to the antiferromagnet in your results, but not to the pneumatic? I mean, do you theoretically understand that?
Yeah. There is a hint that we didn't realize, and I swept under the rug here. So let me mention that. I mean, the full answer is I don't know, but it's somewhat of a bad coincidence. So the antiferromagnetic transition that we studied here was an easy plane antiferromagnet. It was an O2 antiferromagnet, and it turns out that at least the leading order vertex correction, which is the thing which is kind of beyond Hertz-Millis, vanishes exactly for that type of order parameter, but not for O3 or O1. Okay, so that's very special. So it might be that this is actually an accident, and we're now studying O3. But yeah, I mean that's also a statement about perturbation theory, so it's not the full answer.
But on the other hand, your result for the electron self-energy is entirely inconsistent with Hertz-Millis, even in this problem.
Yes, absolutely.
How close is alpha equals 1.5 to what you actually expect in the system?
Yeah, right. So once again, the real answer is I don't know, but alpha 1.5, say order 1, means basically that the coupling constant is of the same order as the Fermi energy. Okay, so now in solid state physics, there are actually very, very few small parameters. At zeroth order, everything is of the order everything else. Okay, so it's not, a priori, it's not crazy, but yeah, but we haven't tried at all to be quantitative about it. We just, yeah.
Let me ask a technical question. How big are your systems and how much computer time went into those pictures?
Right. So the maximum system size in the pneumatic problem was 24 by 24 at temperatures of order 100th of the Fermi energy. And the antiferromagnet is actually somewhat smaller because of the fact that we have to do this doubling of degrees of freedom. That actually slows the calculation quite a bit. So the maximum is about 16 by 16, same order of temperatures. Now, we're quite convinced that even though these sound actually pretty small systems, we're actually pretty convinced that what we're seeing is not finite size effects. It cuts off the length scale is actually this superconducting scale, not our system size. And it's millions of CPU hours that go into this in a few years.
What sort of temperatures does the data actually get down to?
Right. So the natural energy scale here would be the Fermi energy. So we can get to 100th of the Fermi energy fairly easily. Okay, and the maximum TC that we ever see, so the maximum TC pretty much both in the antiferromagnetic and in the pneumatic problem is maybe the Fermi energy over 30 or 25.
One more question.
So initially you showed the phase diagrams of two breaks in RF superconductors.
and you've shown the results for the pneumatic and magnetic critical points,
Yes.
but only in the iron-based superconductors. I mean, you were simulating the case of iron-based superconductors.
Well, I mean, I wasn't really simulating any particular material. I've actually sort of took two ordered phases that definitely occur in the iron-based superconductors and sort of imagined that I can have an isolated critical point of that type. Okay, so this is sort of a first step. An obvious thing to go sort of closer to the actual physics of the iron-based superconductors would be to try to combine them to see what happens when both of them occur close to each other. Yeah, so we kind of rely here. We're definitely not trying to capture the microscopics of any material.
Sure, but my question would be, did you try to do these simulations also for a case that's closer to the cuprates?
Right, so no. Well, I mean, yeah, so let me, yeah. No, I mean, it's the antiferromagnetic critical point is actually fairly close to the electron side of the cuprate phase diagram. Okay, so actually in several senses, there's only one type of strong primary order, which is antiferromagnetic. It's commensurate. Okay, it's at pi, and there isn't seem to be a lot else going on. In the whole dope side of the cuprates, it's a whole different story. Okay, and this is very different from either of what's seen there.
Just have one question. Is there a way to suppress superconductivity near the critical point without violating the sine problem? Maybe in some fictitious way, like a spin-dependent magnetic field or something?
So spin-dependent magnetic field won't do it in principle. It would still...
Opposite fields for opposite
They would still have a pairing instability. The only way I know is this angle between the Fermi surfaces. So there we saw TC reduced by a factor of 2.5.
For the antiferromagnetic.
For the antiferromagnetic. For the pneumatic, we don't know of any way.
So some of my friends would find the fact that we can't kill TC to be a good piece of news. All right.
Just coming back, is there a reason to conjecture that it's actually impossible to have a naked quantum vertical plane in these?
Yeah.
What's the good reason to conjecture it?
Yeah. So there are several ways to say it. I mean, I've never seen it proven, but so this absence of a sign problem is always tied to having some effective time versus symmetry of the action. That always comes with a pairing instability. That's for one thing.
No, I meant more generally. Suppose you had a Fermi surface that was not T-symmetric, and you'll have a sign problem. But I meant
no, I don't know of any reason.
Okay.
Well, yeah, there is a reason, right? I mean, there tends to be a big mass renormalization, which means you've got lots of low energy.
So velocity is 0, and so you have lots of instabilities.
I mean, it's intuitive. It's not a.
It's not a theorem.
Actually, the first problem is to prove that metals exist. After you've done that, then you can worry about the critical.
All right. So with that, let's thank Erez again. Critical points may be easier.
Yes.
Very nice.
No.
Just wanted to ask stupid questions.
By the way,
Actually, maybe I'll turn you off before I ask stupid
Off the record.